Hello, Algebra 2 students. So last time we learned how to solve systems of equations using the graphing method, the substitution method, and the elimination method. Today we are going to learn how to graph systems of linear inequalities. In section 2.8, we learned how to graph linear inequalities in two variables where we graphed using an appropriate form, whether that was slope-intercept form or standard form. We connected dots with either a solid or dotted line, and then tested a point to see whether the region was true or false. We always shaded the true region. We do the same thing for a system. So you do the same exact thing, but you do it for two lines. And instead of shading, we're going to draw arrows to indicate a true region. And then at the very end, we are going to shade the intersecting region. So let's look at the example on the far right. So we have two inequalities. We have inequality number 1, which is y is less than or equal to 3x minus 2. That's going to be solid. The slope is 3 over 1. We go up 3, right 1, and the y-intercept is 0, negative 2. For the second inequality, this one is dotted as there is no line under the inequality. The slope is negative 1 over 1, and the y-intercept is 0, 4. Let's graph inequality number 1. So inequality number 1, we start at 0, negative 2, go up 3, right 1, repeat edge to edge. Connect the line with a solid line, and then we test a point that's not on the line. So we want to test 0, 0. Always test your point in the original inequality. So y 0 less than or equal to 3 times x, which is 0, minus 2. 0 less than or equal to 0 minus 2. That is false because we know 0 is greater than or equal to negative 2. So 0, 0 is false. Therefore, all the points on that same side of 0, 0 is false. This is the true side. So we don't shade the true. We just draw arrows indicating where we would be shading. And then we do inequality number 2. So that one, we start at 0, 4. And then we go down 1, right 1. Notice where the two lines meet is not going to be the solution because these are not equations. This one, you're going to connect it with a dotted line. And again, we can test 0, 0. So I'm going to test 0, 0 in inequality number 2. So we have 0 greater than negative 0 plus 4. 0 greater than 4, that's false. So 0, 0 is false. This side would be the true side. And now if we look at step 3 in the steps for graphing, it says shade the intersecting region. Well, the intersecting region will be where the red arrows and green arrows meet up. And that would be this top right portion. So all of this where the green arrows and the red arrows meet. And that is your answer. Although any point in that region will satisfy the inequalities. And that's how you solve a system of linear inequalities. Let's do a couple of more examples. So example number 1, it's already in y equals mx plus b form. So slope is negative 2 over 1, and the y-intercept is 0, negative 3. The line is dotted. Inequality number 2, we want to either use x and y intercepts or do slope-intercept form. And since students like slope-intercept form, I'll stick with that. So we have 2y is greater than or equal to negative 4x plus 8. Divide everything by 2. Y greater than or equal to negative 2x plus 4. Slope is negative 2 over 1. Y-intercept is 0, 4. And that is a solid line, so greater than or equal to. Okay, we are going to graph inequality number 1. So start at 0, negative 3. go down 2, right 1. Okay, connect that with a dotted line. And then test a point that's not on the line. And 0, 0 is not on the line. So I will test right here. Notice I labeled it number 1, so it's always dealing with inequality number 1. So y is 0 less than negative 2 times x minus 3. 0 less than 0 minus 3. That's false. So 0, 0 is false, and every point on that same side is false. So this is true, because 0, 0 is on the other side. And now we are going to graph inequality number 2. So start at 0, 4. Slope is down 2, right 1. Connect it with a solid line. Hardest part for me is connecting the dots. And now we can test 0, 0 since it's not on the line. So 4 times 0 plus 2 times 0, is it greater than or equal to 8? The entire left side is 0. 0 greater than or equal to 8, that's false. So 0, 0 is false again, and this side is true. If we look here, this is going to be a no solution because the arrows will never meet. Now, that's not always the case for two parallel inequalities. And the reason why is they're not equations. If they're equations, there will always be no solution if they're parallel. But sometimes you do have the intersecting region in the center part. Okay, now we will do example 2. So for this particular one, we need to put both inequalities in y equals mx plus b. So inequality number 1, we have y greater than negative 1x minus 3, m equals negative 1 over 1, b equals 0, negative 3. So you go down 1, right 1, and it's dotted. Inequality number 2, it's also dotted. This time we want to add 6x to both sides. Please don't accidentally call that 7x. So y is less than 6x plus 1. Slope is 6 over 1. You go up 6, right 1, and your y-intercept is 0, 1. And we are ready to graph each one. So starting with inequality number 1, we're going to plot 0, negative 3. And the slope is negative 1 over 1. So down 1, right 1. And that one we connect with a dotted line. I guess both of them are dotted. Let's test 0, 0. So test 0 plus 0 greater than negative 3. 0 is greater than negative 3. That is true. So 0, 0 is true. So just point to the 0, 0 region, the true region. And now we are ready to test the second inequality, which is negative 6 times 0. You know what? I didn't even graph it. So let's graph it first. So start at 0, 1. Go up 6, 2, 4, 6, right 1. And from the y-intercept, go down 6, 2, 4, 6, left 1. Connect it with a dotted line. Now this one, the way I drew my dotted line, 0, 0 looks like it's on the line, and it really isn't. But let's just, for the sake of this problem, test something that's not 0, 0. Let's do, let's test, so I'm going to erase this right here, because we want to pick a different point to test. And I think we should test this point right here, 2, 0, because it's not on the line. So remember, x is 2, y is 0. So in our original problem, it's negative 6 times x plus y less than 1. So that's negative 12 plus 0 less than 1. Negative 12 is less than 1. That is true. So we want to point to that point because that's true. This is the true region. And notice where the red and green arrows meet is the intersection. That shaded region is the solution. So this entire region right here. Should have drawn more arrows. Always draw enough arrows so you know that you don't miss something that you're shading. Okay, now going to example 3, we are not going to do that particular one because it ends up being just like example 1 and we just don't need to do it. But we should definitely do example 4 because it has 3 inequalities. So it's a good one. So example number 4, if you look, all of them are dotted because none of the inequalities have a line underneath. Let's label this inequality 1, inequality 2, and inequality 3. For inequality 3, it has 2 variables, so that's in slope-intercept form. So here the slope is, that's a 1 over 1, and the y-intercept is 0, 0. But for the other two, instead of guessing what the lines look like, it's best to make a table. So for inequality number 1, temporarily change the inequality to an equal sign and make an xy table. Notice x equals 6, so it has to be 6, and it can't be any other number. Y can be any number you want it to be. And so let's just pick a negative number, a positive number, or 0, and some positive number. And let's do the same thing for inequality number 2. So temporarily change that to y equals -1. This time y is -1 because it tells you y equals -1, and x can be any number you want it to be. So let's just pick -1, 0, and 2. And we are ready to graph. So we'll start with inequality number 1, and we're going to plot those ordered pairs that are in the table. So 6, -1, 6, 0, and the last one was 6, 2. Connect those with a dotted line, and then you can clearly test 0, 0 because it's nowhere on the line. So we are going to test 0, 0. When we test 0, 0, make sure you test in your original inequality, which is x less than 6. So 0 less than 6. We don't even need the y coordinate, and that's true. So the true side is the side that 0, 0 is on. Okay. Now let's do inequality number 2, -1, -1, 0, -1, and 2, -1. That's also a dotted line. And we can test 0, 0. So when we test 0, 0, 0, y, which is 0, greater than -1, that's true. So 0, 0 is on this side of the line, and it's true. And lastly, we are going to plot or start at 0, 0, and then we're going to go rise 1, run 1 to the right. Notice for this one, we cannot test 0, 0 because 0, 0 is on the line. So we have to pick another point. You have no choice. And so I say we pick something like here. Let's pick that one, 0, 3. So this is x, this is y. So y is 3 less than 1 times x. So 1 times 0. So 3 less than 0, that's false. So that point produced a false statement. Therefore, this is the true side. And notice the region where they intersect is this little triangle right here. That's where the green arrows, the red arrows, and the blue arrows meet. So solving systems of linear inequalities is pretty similar just to graphing a linear inequality in two variables, but you have an intersecting region. And those are your notes for today. Have a great day, Algebra 2 students.